Okay.
So Aman, I was like, what is?
Aman, when are we doing the test?
Oh.
No.
Okay, here we go. What was day one of 5.6? Do we remember?
Going from position to velocity.
No.
No, it wasn't.
The fundamental theorem of calculus. Thank you, Cody.
We already do that. Like, we had a quiz over that. He said what was the part one?
Yes.
Oh,
Yep. We did take a quiz on 5.6 day one already. Fundamental theorem of calculus, which we just exercised on the backboard back there. You guys were really good at it. It was pretty straightforward. Okay. But there's a couple of other theorems that we can get from the fundamental theorem of calculus, very simply, that we're going to address today. First is going to be what we call the mean value theorem for integrals. And before I flip to that next slide, I know you guys already have, it's no big deal. But let's remind ourselves, because we had a mean value theorem already, right? But it was for what? Derivatives. What did that theorem state?
The secant line has a tangent point that's equal to it.
Nice, Jay. That was basically the upshot of the theorem, right? Your function had to be continuous on a closed interval, differentiable on the open. And then if that was the case, there was some point C such that the slope of your tangent line, which was instantaneous rate of change, was equal to the slope of your secant line, which was average rate of change, right? So then we did f of b minus f of a over b minus a. We set that equal our derivative, and then we produced a c value that made that happen, okay? All right, so mean value theorem for integrals works in a similar fashion. We have a function that's continuous on a closed interval. Then if that's the case, then there is at least one x value in that interval such that the integral from a to b of f of x dx is equal to f of x star times b minus a. We've seen expressions that look like the right side of that equivalency in the past. What does this remind you of? F of x star times b minus a.
Like the equation for exact area under the curve.
Yeah, I mean, that was very similar to the equation of exact area under the curve, which was like your function value multiplied by your change in x. And what did we use to first estimate those areas? Rectangles. Do we recognize this as being just area of a rectangle? F of some value is going to give you your height. B minus a gives you your base, okay? So that's what that part underneath says. In other words, there's always, so like an integral represents area under a curve. This tells you that there's always some rectangle that has the same area as the region under the curve. And we can find those values by using the function, okay? All right, so let me illustrate that point. So given that f of x is equal to x squared on our closed interval from 1 to 4, find the x value guaranteed by the mean value theorem for integrals. And I feel like I have to check this now because I feel like this is incorrect. But when we do mean value theorem, I think your value has to be on the open interval, not the closed interval. So let me double check real quick. Should know that off the top of my head. No, it is in the closed interval. I always thought it was open. Okay, either way. This process, I feel like, will be very natural for you guys because we just need to take our definite integral of our function on the interval that they give us. So we're going to do the integral. So I'm going to state it real quick. Integral a to b f of x dx is equal to f of x star times b minus a. Plug in what we have. Integral from 1 to 4 of x squared dx is equal to, I'm going to leave this as f of x star for now. But then b minus a, we can plug that in to get 4 minus 1. Okay, you can think of like these three pieces as being like three separate quantities. I can find, so let's say it's number 1, number 2, number 3. I can find number 3 real easily just by using my interval, 4 minus 1 in this case. Number 1 I can find as well too. That's just the value of my definite integral, okay? And so number 2 is essentially what we want to isolate and find because we want to find the x value, we want to find x star, okay? All right, so if I integrate the left side, 1/3 x cubed evaluated from 1 to 4. I'll figure out what that is in a second. of x star on the right times 3. So then we evaluate 1/3 times 4 cubed minus 1 cubed. F of x star, and then times 3. All right, 4 cubed, what is that? Times 4 times 4, so we get 64, right? So then 64 minus 1 is going to give me 63. So 1/3 of 63. I'm going to annoy you with how many steps I show. It's not meant to be insulting. All right, so 1/3 of 63 is what? 21? Times 3. So then, yeah, divide both sides by 3. And we get that 7 is equal to f of x star. All right, so that's going to become important in a second. So that's f of x star, but I want to find what x star itself is. I need to find that x value. How could I do that? Max?
Square root of 7.
Pretty much. You said plug it in. Is that what you said, Ellie?
I didn't say anything.
You said that, Kira? Yeah, so let's take x star and let's plug it into our function itself. So if we do that, we would get 7 is equal to x squared was our function. And then Max was just saying, okay, we'll take the square root of both sides, and you get x star. So x star squared, I guess I should say, is equal to, let's say plus or minus square root of 7. But do I want plus or minus? We always have to be careful. Do I want both the positive root and the negative root? Why not the negative? It's not in the interval. Very good. It's not that I can't have negative values. It's just that it's not in the interval. Okay? All right, cool. So there's our x value that guarantees it. Now, let's look at what that means from a visual representation. So we're going to sketch a graph. We're all going to sketch a graph. All right, so interval is from 1 to 4. And then we're going up there. So if I graph x squared on the interval from 1 to 4, let's see, I got the coordinate point 1, 1, and then my other coordinate point would be 4, 16. I don't like that point. Let's shift that to the right a little bit. So my function looks like this. Hey, that curve doesn't look that bad. So we are getting this area right here. All right, so then there's my area under the curve, okay? What I'm telling you is we can generate a rectangle that has that same area using those values that we looked at already, okay? And those values that we found become very important. Where does, for the height of my rectangle, what x value do I need to take the height of to find the height of the rectangle that's going to have the same area? Well, my base is going to be 4 minus 1. My base is going to be 3. For the height of my rectangle, that happens at what x value? Square root of 7. That's the x value that's going to give me the height of my rectangle, right? What was the height of my rectangle? Well, we set up here for the result, this represents height of my rectangle, right? This was base. That's going to be 3. It's no big deal. But f of x star is my height. Didn't I find what f of x star was? I did. That's right here, right? So then the height of my rectangle is going to be 7. 1, 2, 3, 4, 5, 6, 7 is here. That is f of x star. Okay. That height happens at the x value of square root of 7. What is square root of 7? It's like 2 point something, right?
Yeah.
2.73 or something like. I don't know what it is. I'm not sure. Either way, 1, 2 happens like right. I don't know. Let's just say like right here-ish. Let's say that is square root of 7, which is our x star value. Okay. So if I take the area of the rectangle that has a base of 3, but this height, this theorem is saying the rectangle that's in the blue dotted area would be the same area as the red area that is under the curve. Does that seem like it would be feasible? If you look at the area of the rectangle, there's some overestimation and some underestimation, right? So I could say, I don't know, if I cut this top part off, like up here, like, you know, that part, and then I put it like where that overestimation is, probably fills that out, okay? So that's what this theorem is saying. Okay? All right, questions there?
Is it like 100% or is it like the weird squiggly, like kind of basically?
100%, man. 100%. Okay, let's do it again. But let's say our function is square root of x. All right, so we're going to do integral from 1 to 4 of square root of x dx. And we're going to set that equal to f of x star times b minus a, which is just going to be 4 minus 1. So again, just me using the statement of that theorem. All right. So x square root of x is just x to the 1/2. So then when I take my antiderivative, it becomes x to the 3/2. We're going to multiply it by 2/3. Don't forget to take reciprocal of that fraction. And then we're going to evaluate it from 1 to 4. Still set that equal to f of x star and then times 3. It's helpful to figure out what f of x star is before you actually set it equal to what that function is. Because like I said, if I ask you to, you know, make a graph of that, then it's good to have that value on deck. All right, so 2/3, and then we're going to do 4 to the 3/2 minus 1 to the 3/2 times 3. Might as well drag that 3 over to the left side and make it 2/9. And then inside of that set of parentheses, square root of 4 gives me 2. 2 to the 3rd power is 8. 8 minus 1 is going to give me 7. Two ninths times 7 is going to give me 14/9. And that is my value for f of x star, which we saw that that value was important, okay? But now I need to figure out what x star is. So I'm going to set 14/9 equal to what? Good. I'm going to say square root of x star. And then I just need to square both sides. So I would get that x star is equal to 196 over 81. I just put a number sign. Good at making stars. There we go. Oh, my stars. So we get that x star is equal to 196 over 81. Okay. Now, let's make a graph. All right, so our interval is from what? 1 to 4? 2, 3, 4, space it out. My outputs aren't going to be very high. Square root of 1 is 1, square root of 4 is 2, so let's say 1, 2. All right. So we would have 1, 1, and then 2, 4. So my function is going to look something like this-ish right here. All right, so then my area is going to be there. So that's my area under my curve. So then now, I want to draw my rectangle in. Let's get some practice doing that. Okay, you tell me. How do I do this? How do I draw my rectangle? It's got to be between 2 and 3. That comes from the 196 over 81, right? So 81 times 2 would give me like 162. 196 is over than that. So Rohan's right, somewhere between 2 and 3. And then what is my height? 14 over 9. So that's somewhere between 1 and 2, right? It's like 1 and 5/9. So a little over half, right? Okay. So we're going to say that this is 14 over 9, which is f of x star. And then Rohan said somewhere between the two is where we would actually have that height, the x value that gives us that height. So then we're going to say this is x star, which was 196 over 81, which I believe is relatively prime. Okay, so then my height is here. Something like this. And then when I shade that in, give us a nice little purpley color. Boom, looks like that. Rectangle looks like it's got an overestimation, underestimation on either side. I feel like those values would fill each other out if Mr. Pacifico was better at making graphs. So I would believe that to be reasonable. All right, do we understand the graph? In case I ask you to reproduce a graph on a high stakes assessment? Yeah? Great. Okay, cool. Average value theorem. So we did mean value theorem already. There's also something called average value theorem. I believe your book actually gives it a definition instead of calling it a theorem itself, okay? Which it's really easy to prove, so I guess I could see why it would be considered a definition. But honestly, it's very similar to what I just gave you guys. If you have a function that's continuous on a closed interval, then the average function value, or average value of f, or mean value of f, on the closed interval a to b is defined as f with a subscript average, AVE, fave, equals 1 over b minus a times the integral from a to b of f of x dx. Isn't that insanely similar to what I just gave you guys? What was the only difference? Yeah, b minus a, if I multiplied it to the right side, it was just, it was over on the right, okay? So, and then there was that f of x value, which we are going to consider to be our f average, okay? All right. So, in that case, really what this is equal to is, it's important to call this out, but what this is equal to, f average is just equal to f of x star. Because if I use the theorem from last time, if it was f of x star times b minus a, if I just divide both sides by b minus a, I get, the result that I have in front of me, okay? So f of x star represents your average function value of that function on that interval. Let's do it with a function we already did it with, just to ensure that it's all the same. So if I integrate 1 over b minus a from a to b of f of x dx, I would get 1 over 4 minus 1 integral from 1 to 4 of x squared dx. And let's see what we get. So I get a third. And then antiderivative of x squared is 1/3 x cubed. We saw that already. Evaluated from 1 to 4. So I would get a 9th times 4 cubed minus 1 cubed, which is a 9th times, that was 63 previously. Yeah, so it ends up being 7 because you divide it by 3 2 times. So we get that our f average was just equal to 7, which we saw before was what f of x star was equal to. True or false, my handwriting is getting better with this. Compared to the beginning of the year, it's definitely better. All right, cool. Let's do the same thing with square root of x, show that it's the same, and then I'll be done talking at you. So 1 over 4 minus 1, want to do average value again, integral from 1 to 4 square root of x dx. One third. And then our antiderivative, so it's x to the 1/2. So we would have x to the 3/2 multiplied by its reciprocal of 2/3, evaluated from 1 to 4, which gives us 2/9. And then inside of our parentheses, we would have 4 to the 3/2 minus 1 to the 3/2, which is 2/9 times, okay, so 4 to the 3/2 again was 8. And then 8 minus 1 gives us 7. So we end up with 14/9 is equal to our average function value. Also known as, do we remember that value from f of x star before? Cool. What's that? If I find that x value was 196/81. But our function value was just 14/9. If we go back to here, that represents a y value, and our y value was f of x star right here was 14/9. So that's on our graph right there. Okay. All right, questions there? Your homework is split across 2 different pages because average value theorem, definition, whatever you want to call it, is actually a concept out of chapter 6. It's in section, I think it's 6.6. So page 359, 54, 53, and 54 is mean value theorem stiff. And then 1 through 9, 15, 16, and 23 is questions related to average value theorem. Okay? All right. Tomorrow is Saturday. And then on Monday, we're going to do the last part of this section, which is fundamental theorem of calculus. It'll take us some time to get through that because I have like 6 or 7 examples cooked up for you guys for those. So it's going to take us some time to get through it. But some of them are kind of short. So, okay? All right. Tuesday quiz, Friday test. Our schedules are busy. Get some